Hello, this is MEI Further Maths Core Pure. We're in the third complex numbers section and on the fifth video on modulus definitions for loci. You can watch the video straight through, but you will probably find it helpful sometimes to pause the video and try things out for yourself before continuing to watch. Consider the set of points z such that the modulus of z minus 3 is equal to 2. What does this set of points look like? Pause the video now while you think about it. OK, this is the set of points which is a distance of 2 units away from the point 3. So we could take 5 take away 3 is 2, which has modulus 2, or 3 take away 2i. Subtract 3 gives us minus 2i, which has modulus 2, and so on. All of these points satisfy that equation. And of course, we have a circle. It has centre 3 and radius 2. What about this set of points? Pause the video for a moment while you think about it. OK. This time we're looking at the set of points which is 3 units away from the point 1 minus 3i. So it could be that point, or this point, or this one, or this one. All of these points satisfy the equation. And again, we have a circle. This time it has centre 1 minus 3 and radius 3. We can look at this algebraically. Z1 is a fixed point, x1 plus I, y1. Z equals x plus iy is a variable point, and we want to find out which values of z satisfy the equation. We're looking for the points z which are r units away from z1. We substitute in to z minus z1, z equals x plus iy, and z1 equals x1 plus iy1. We then collect real and imaginary terms, and we find the modulus of our number. That needs to be equal to r. If we square both sides, you can see that we've got a circle with centre x1, y1 and radius r. Here's another example. Find the set of points for which the modulus of z minus 3 minus 4i is equal to 5. We need to have this in the form z minus z1 is equal to 5. So I need some brackets. Z take away 3 plus 4i. Then just double check that what you've got now is actually the same as what you had before. So we're looking at the set of points which are 5 units away from the point 3 plus 4i. It's a circle, centre 3, 4, radius 5. Notice, of course, that this circle goes through the origin because we've got a 3, 4, 5 triangle. Now let's look at loci of a different form. Here we've got 2 fixed points, z1 and z2, and we're looking at the set of points z such that its distance from z1 is the same as the distance from z2. Pause the video for a moment while you think about what that will look like. OK. There's a sample point, 1 point from our locus. We're looking for all the points that are the same distance from z1 and z2, and that's going to be the perpendicular bisector of the line joining z1 and z2. Here's another example. As before, the first step is to rearrange the moduli to be in the correct form z minus z1. So that's going to be z minus, well, I need plus 3, so that will have to be minus 3. And I want minus 4i, so that will be z take away, brackets, minus 3 plus 4i. So my point z2 is minus 3 plus 4i. So there are the 2 points, and I want the perpendicular bisector of the line joining them. So we've sketched the line. Can we find its equation? Well, as we did with the circles, we can just substitute for z in that equation and see what we get. So let z equal x plus iy. So x plus iy minus 3, modulus of it, is equal to x plus iy plus 3 minus 4i, modulus of it. We'll tidy it up by collecting real and imaginary terms. So I've got x minus 3 plus iy on the left, and on the right I've got x plus 3 and I times y minus 4. I can usefully put brackets around these bits, not because I need them, but it helps to clarify things. Now I'm going to find the modulus of these numbers, but I'm not going to bother square rooting because I do that on both sides and they'd still be equal. So I'm just going to square the real part and square the imaginary part there, and that's equal to the real part squared on this side plus the imaginary part squared. And of course the moduli are equal to that square rooted, and I'm just squaring both sides. So here I get x squared minus 6x plus 9 plus y squared equals x squared plus 6x plus 9 plus y squared minus 8y plus 16. So cancel the x squareds, cancel the plus 9s, cancel the y squareds, and I'm left with 8y on the left and 12x plus 16 on the right. Dividing by 8 gives me y equals 12 over 8x plus 2, or y equals 3 over 2x plus 2. And you can see that that is indeed the equation of the line that we've got. There are more notes on integral on modulus definitions for loci. That's the end of this short video. The next video in this series is on argument definitions for loci.